Yeah, good morning, ladies and gentlemen. I thank the organizers for their kind invitation to this meeting. And in my talk, I will address several aspects of a mobility based on various alternative options for drivetrains. My name is Maximilian Fichtner. I'm director at the Helmholtz Institute Ulm, which is a battery institute. And I've worked for 12 years on hydrogen drivetrains with fuel cells before I came to that position. Now, the reason why we gather in meetings like the one today is actually a situation which is roughly depicted in this diagram here. This shows the use of fossil fuels of mankind over the years from a historical perspective. So if we allow us to step a little bit back and look at what has happened in history, we will find in a few hundred years that it's most likely happening like this here. We have here a singularity which actually shows that there's a large peak where mankind has used fossil fuels to a great extent until the storages slowly ran empty, and there has been a decline in the following decades and maybe hundreds of years. So this is something which we will have to encounter. Some people say we are exactly here on the top. Some people say we are a little bit behind or a little bit before. I would say from a historical perspective, this doesn't matter. This is a situation we will be facing. What is now one of the most challenging aspects here for us scientists and also engineers is that we have to somehow fill this gap in order to keep our living standard, to be able to be mobile and warm our houses. So this is certainly one of the greatest challenges mankind has ever encountered, and this is the reason why we are speaking of a great transition in history also. Now, this is of course a situation which bothers many people, and many people would therefore like to conserve the technology they have been using so far, and therefore would like to continue with cars based on a combustion engine, which is then running on so-called e-fuels. What are e-fuels? E-fuels exist. They can be made from carbon dioxide that is collected from the atmosphere. They are made from hydrogen, which is obtained by water splitting, electrical water splitting, and of electrical energy. Yeah? So from these resources, you can make such liquid fuels, and with those you can propel various applications like trucks or cars, airplanes, ships, and you can even heat your household. So far so good. There's a downside in that technology, and that is it's extremely inefficient actually. I just have one example here. The production of 1 liter of such an e-diesel from CO2 and hydrogen consumes 27 kilowatt hours electricity according to recent numbers. Now we all know that a diesel car roughly consumes 6 to 7 liter diesel on 100 kilometers. That makes a total of 162 kilowatt hours needed for 100 kilometers range. Yeah. Now, I don't know how many of you are driving an electric car, but with that amount of energy, a battery car can drive 1,000 kilometers. Yeah? And still you have local emissions, you have the soot, you have still NOx, and you have noise. And this is a problem. And last but not least, because you need a tenfold amount of energy compared to the pure electric application, tank filling is very expensive. You would have to pay at the moment 300 or 350 euros per tank filling, and this is without tax. So this is probably not a competitive option at the moment. Any other option would be by far more cheaper. So Keeping the internal combustion engine as an option would mean that we keep all the drawbacks that are associated with this technology, and we would buy just the convenience of going on with the same type of cars by a tenfold amount of energy that we would actually need. And this is the reason why many people have thought about alternative options, and in the following I will compare two of them. It has been shown in many studies that electric drivetrains are by far the most efficient option for propulsion of cars. Basically, there are two technologies which have been developed. One is shown here on the left. Here, a source of renewable energy like sun or wind is used to produce electrical energy, and this energy is stored directly on board of a car in a battery, and then is transferred to the electric motors at the wheels. The second option stores this energy in a chemical compound, here hydrogen as an interim storage. Now this hydrogen needs a bit of a technology chain before it can be used in a car and converted back to electricity, and on the following slides I will say a few words more on these two options. Also here there are quite some differences between these two technologies, and I just would like to compare them on such a basis where we see the energy from a windmill, for example, going into a pipeline which is leaking here and there depending on the step of the technology. So the wind energy that is generated here doesn't need any processing. It certainly will suffer from some transport losses in the electrical grid. Then you have some losses when you charge and discharge the battery. This is around 10 to 15%. There's no further conversion needed. The electricity goes directly to the electric motor, so that at the end of the chain, about 70% of the energy that once has been generated here is coming out of this pipeline. So this is the energy which goes onto your wheel of your car. If we are now comparing that to the hydrogen option, we can do the same Gedankenexperiment. We have 100% of energy coming from the windmill. The first step that we have to do is we have to generate hydrogen with an electrolyzer. This is the device that splits up the water into hydrogen and oxygen. And if you run such an electrolyzer in a wind park, for example, this is not very much efficient because you have load level changes, and this is quite unhealthy for the electrolyzer, so that you have an efficiency in the order of 50 to 60%. That means you lose in better cases 40% in the production of the hydrogen. Then you have to clean it up and pressurize it to 250 bar for the transport. This consumes another 12% of the energy. If you want to liquefy the hydrogen, so if you want to transport more of the hydrogen, then you have to cool it down extremely deep, and you would lose some 40% of the energy that is contained in this pipeline. Then you lose a little bit during the transport. This is not much. And then you have your gas station. And this is a quite interesting aspect, because I see in none of these recent studies about the efficiency of the hydrogen chain losses of a gas station mentioned anywhere. What is happening there? What we have there is a big hydrogen tank, and in order to precondition the hydrogen for the injection in the pressure tanks of the car, this hydrogen is pressurized up to 1050 bars and cooled down to minus 40 degrees. And this is also very, very energy costly, so that in such a case you lose in the order of 30 or 40%. This is, as I said, often not taken into account in these studies. Then we have the conversion on board of the fuel cell. The efficiency is about 50%, and there's a little bit loss, like in the other example here. You have the electric motor, and at the end of the pipe you have some 15 to 18% left. That means this is a technology which basically works, and it has been tested many times. But in that case, if you would like to produce the hydrogen somewhere in your country, you would need by a factor of 4 more windmills or solar panels in order to generate the electricity which drives this option compared to the pure electric drive. I have here a slide which is maybe more relevant for decision makers or politicians, and I would like to compare 2 basic scenarios. One is a scenario where we replace all of our 47 million cars at the moment in Germany by battery electric vehicles, and in the second case I replace all these cars by hydrogen cars. Now, in 2018, our current transport sector consumed 750 terawatt hours provided by oil and gas. Now, if I do the first calculation and look at the scenario for the battery electric vehicles, this trickles down to 130 to 170 terawatt hours, which are required to run the entire system. If I do the same with hydrogen based fuel cell cars, I need more energy. This is about 1,000 terawatt hours, and this number comes from the fact that the entire chain, as I showed you before, has an efficiency of 15 to 18%, while the combustion engine, diesel engine for example, can be calculated as something having between 20 and 25%. So in total you would need much more energy, and I don't see how this can be provided at the moment. Nevertheless, a hydrogen society is not impossible. It all depends on the question on how much hydrogen can be made available, how much green hydrogen, and whether it's possible to bring down the costs in each part of the chain by a factor of 3. In addition, there are a couple of other issues that need to be solved in order to make this a viable option. I have here a list of them. We cannot go into detail on all of them. Let me just pick a few of them. One is, for example, that a hydrogen delivery truck brings hydrogen for about 60 to 65 tank fillings of fuel cell cars. That means every average gas station would need an own fleet of about 5 trucks per day. And also, this is absolutely correct, you can fill your tank within 5 minutes only, 3 to 5 minutes roughly, but only every 35 to 40 minutes, because the gas station needs time for recovery for the next customer. And then there are another of things which are maybe not so practical for a user. For example, if you have, I say, Hyundai Nexo, for example, you need to visit the garage every 10,000 kilometers for a thorough safety check. This is not necessary with other cars. And then there are also some safety concerns. If you take fires, for example, in the US, there are 5,000 garage fires every year, and if you have a hydrogen tank in a car inside such a burning garage, there's a safety mechanism which opens the tank, and about 4 cubic meters per second hydrogen are going to be released into the fire, and just by the pressure that is building up in the garage, within 1 second the pressure limit of civil buildings would be exceeded. And because in addition the hydrogen will explode, this garage will definitely be flattened, and most probably the house next to it also. And then let's just keep in mind that currently the hydrogen is not green, and the CO2 footprint of the hydrogen that we are using today is 2 times that of a diesel car. Yeah, so this is not an option to improve the climate situation at the moment. Yeah, but also the battery technology is not free of criticism. And there are also problems that need to be solved. And one of the most frequently mentioned issues in that field is the use of the raw materials. And I will comment on that in the next few slides. As most of you may know, lithium-ion batteries have been based on the use of cobalt. Cobalt has been used in the cathode since the beginning of the lithium-ion battery in 1991, where cobalt oxide was used as the cathode material in the battery. This is still the case for cell phones and notebooks, where we still have this more or less pure cobalt oxide. For car batteries, there has been a very long and great development in order to reduce the cobalt content, because it has been clear more or less from the beginning that cobalt is expensive, it's toxic, and later it also has come out that it is associated with child labor, for example. This is why internationally there have been efforts since the 1990s to get the cobalt out of the battery. And it seems that this is going to be successful. Tesla has reached a cobalt content of 2.8% in his recent models, and now the first models are coming up which are based on lithium iron phosphate. And these batteries, they contain neither cobalt nor nickel nor any other of these toxic or expensive transition metals. This is one example where a car manufacturer, in that case Volkswagen, which collaborates with a Chinese company named Godian, has developed a drivetrain which is not based anymore on any cobalt or nickel containing compound, and I would regard that as a progress. Here we see how the capacity of such cells is steadily increasing, and there are some other advantages. It's not only that there's no cobalt, no nickel, there's also no thermal runaway, so these batteries will not really catch fire. They are safe in nail penetration tests, and they can be charged and discharged 10,000 times. That means such a battery enables a lifetime of the car of 3 million kilometers. Another issue which is frequently discussed is the lithium production, which is associated with water consumption. It is in fact the case that lithium is produced from salt brines, so the salt water of a salt lake in Chile, for example, and for the production of a 60 kilowatt hour car battery, about 6 kilograms lithium is needed, and that means the production of lithium for one car consumes about 4,000 to 5,000 liters of water, which is evaporating from this brine and leaves behind these salt piles here. So this sounds really a lot, 4,000 to 5,000 liters, but we should maybe not forget that we consume very similar amounts in our daily life. So if we take that as a comparison to the water consumption of other products, this is the same amount of water that we use for the production of 250 grams of a beefsteak, or half of a jeans. The cotton needs a lot of water, or 30 cups of coffee, or 10 avocados. So water is needed, definitely, but we should maybe not forget to put that in a relation. In that respect, it may also be interesting to look at the main consumers of water in these arid regions, because this is not only the lithium industry alone. We have here SQM and Albemarle, they produce lithium, but we also have BHP and Zaldívar. These companies are producing copper there since decades, and interestingly, the groundwater level in that region is dropping since the 1960s. Yeah? So if we compare the actual freshwater consumption plus the water rights here at the Salar region, the amount of water spent for the lithium production is by a factor of 8 less than the amount of water that is spent for the copper production just in the next valley. And interestingly, the lithium production consumes as much water as the hotels spend. Yeah? So this is the real production here. These are the water rights. And this is about what the hotels are spending in that region. Last but not least, a major argument against the battery has been that the production of the battery itself produces a CO2 footprint which is higher than that of a diesel engine-driven car, for example. This is correct. There is a footprint at the moment which is higher than that of a car with combustion engine. However, due to the fact that you consume much less energy, and in your electricity mix there's only 1/3 still contained fossil fuels, there is hardly an increase of the footprint anymore, and you will be overhauled by the footprint of gasoline and diesel cars already after 20,000 kilometers. And with the new factories in Sweden and in other places, from the beginning 100% renewable electricity mix will be used, so that you basically do not start from here, but you start somewhere from here. Yeah. So you start with a lower footprint from the start on, which is then hopefully kept at this level by using 100% renewables in the electricity mix. So my last slide is about the costs of battery cars, and there has been a tremendous development in the past 10 years because the costs of a battery dropped by 90%, and this is a still ongoing process. So what we have encountered here over the past 10 years led us to a situation where we are now in the position to say that the battery cars are going to be cheaper than the classical cars with combustion engine. The first cars have already been announced for 2022. Others will follow because this cost curve is still declining. So in the future, battery cars will not only be better, more environmental friendly and have a longer lifetime, they will also be cheaper than our conventional option. So I come to the end, and I have here some take-home messages for you. Electric drivetrains are already now the most safe, energy efficient and cost-effective option already today, especially if you take into account the total cost of ownership. Hydrogen applications currently suffer from a lack of infrastructure, high cost, low efficiency and certain safety risks. E-fuels may be needed for airplanes and maybe some ships, but are very expensive and currently not economically viable for passenger cars, and I also do not see that coming. With that, I'm finished. I would like to invite you to visit one of our websites here where you can learn about what we are doing in our institute and in the collaboration between Ulm and Karlsruhe. And I thank you very much for your kind attendance. Thank you very much.